In this video, we present results from detailed simulations which combine a predictive driver repositioning algorithm with a real-time vehicle route optimizer to dispatch taxi journeys and reposition drivers when they have no pending jobs. Taxi services, restaurant food delivery platforms, and same-day carriers are all types of on-demand last-mile transportation systems. The passengers or goods need to be transported at short notice, as quickly as possible from point A to point B. Speedy delivery is key for these systems. New jobs can be completed quicker if there's a free driver nearby, which raises the question, should a free driver reposition to a different area where new jobs are more likely to come in? For driver repositioning, we need to predict when new pickups will appear. We also need to coordinate drivers, so free drivers don't all go to the same area. This requires a predictive repositioning algorithm. We tested our repositioning and dispatching algorithm against historic taxi trip data and found with predictive repositioning enabled, jobs could be completed in the same average time, but using around 10% less drivers. All functionality presented here is part of the Odio Live real-time route optimization system. A real-time vehicle route optimizer is an engine which generates efficient routes, replans these routes when new jobs are added, and decides when jobs should be dispatched. In the research literature, real-time problems are called dynamic vehicle routing problems. Odio Live is a commercial real-time route optimizer engine that uses an efficient deferred dispatching strategy. For more information, see our previous video comparing deferred to immediate dispatching. Odio Live comes with a simulator tool which wraps around the engine, simulating the evolving planning process and letting a user test what-if scenarios. This video was output from the Odio Live simulator with predictive repositioning enabled. The large stars are the predicted reposition locations, and the corresponding shapes indicate the areas which contribute to their predicted demand. We used Odio Live's new predictive repositioning module to build a predictive model covering weekday mornings in Brooklyn, New York, using public taxi trip data. The built model predicts reposition areas based on both the current time of day and the current number of available drivers, generating areas where each individual area holds work for a couple of drivers. We built the prediction model using data from 10 historic weekdays, and then used the Odio Live simulator tool to test it against the following 5 weekdays. The simulator calls the optimizer around 1,000 times in a single run, and our analysis required 80 different simulator runs. To keep run times tractable, we therefore randomly sampled a subset of historic taxi trips, giving us between 500 and 900 trips per morning, corresponding to a medium-sized taxi company. We ran simulations for different days and different numbers of available drivers, with and without repositions on. With repositions on, if a driver has no jobs, the optimizer can send them to a different location if it estimates there is work upcoming. Without repositions, the driver waits at their last drop-off point. In each simulation, the routing model was configured to use Odio Live's deferred dispatching for maximum efficiency, travel times learned from historic data for maximum accuracy, and ride-sharing was allowed with up to 2 different rides on board a taxi at once. To evaluate the models, we measured job completion time, the time between the passenger ordering the taxi and the time they're dropped off at their destination. As you can see from the graph, we found passengers reached their end destination around 3 minutes earlier on average when predictive repositioning was turned on. Many on-demand transportation providers have service-level agreements based on the average job completion time. This raises the question, how many drivers do I need to achieve my SLA? If we invert the data from the previous graph and interpolate between the points, we get a graph which estimates the number of drivers needed to achieve different average completion time SLAs for our taxi scenarios. Statistics for key SLA times from the graph are reproduced in the table on the right. In all cases, with predictive repositioning, we could achieve the same average job completion time with less drivers. To achieve an average 20-minute completion time SLA, we needed approximately 95 drivers with repositioning off, but only 75 with it on, reducing fleet size by 21%. For a 30-minute SLA, repositioning reduced our required fleet size by around 12%, and for a 40-minute SLA by around 7%. From our analysis, we find that predictive repositioning reduces operating costs, as you can do the same amount of jobs in the same amount of time, but with less drivers. Our scenarios used historic taxi data, but the same model is applicable to any on-demand point-to-point delivery service, including restaurant food deliveries like Uber Eats or one-hour carriers delivering groceries, drinks, or other goods. If you would like more information on our Predictive Repositions module, the Odio Live Optimizer, or have any other questions, please visit odiolive.com and get in touch.